the formula u dot v equals the norm of u times the norm of v times the cosine of theta has a very important corollary. So remember that if u is not the zero vector and v is not the zero vector, then the norm of u and the norm of v are strictly positive. That means that the only way for this dot product to equal zero is if this third term equals zero. That's just the zero product property. Assuming that when you have two vectors, the angle you choose between them is the smaller of the angles as opposed to the larger of the two, there's only one way that the cosine of theta can be zero. And that's if theta is pi divided by 2 radians or 90 degrees. So, definition, two vectors v and w are said to be orthogonal if their dot product equals zero. And the intuition you're looking for geometrically is that these vectors intersect at right angles. In R2 and R3, where you can draw the vectors, that's literally the case. If you move to R4 or R5 or some other larger dimensional space, it's not going to be clear geometrically what a right angle means. Nevertheless, this intuition is going to serve you well. Let's state a definition. So one vector is orthogonal to another vector. We're going to expand this definition so that a vector can be orthogonal to a set. So let's let W be some subspace of Rn. We'll say that V is orthogonal to W if and only if it is orthogonal to every vector in W. And now that we've defined orthogonality to a set, or rather to a subspace, we'll jump right into our next definition and our next piece of notation. So this is called the orthogonal complement of W, and it's the set of all vectors orthogonal to W. Let me end this video with two quick theorems, neither of which I'm going to prove. First of all, the orthogonal complement, is a subspace. Second, the way this is stated, to determine whether a vector is in the orthogonal complement would be quite difficult. You need to check whether it's orthogonal to every vector in W, and there are an infinite number of vectors in W. Never fear, however, we have a useful theorem to deal with that issue. Let's say W has some basis B. I mean, it's a subspace of Rn. It's finite dimensional. It definitely has finite bases. Then a vector V is in the orthogonal complement of W if and only if V is orthogonal to all the basis vectors. And since this basis is finite, we therefore can determine whether or not a vector is in the orthogonal complement by checking finitely many vectors.